Download this code from codegive.com, link in the description below. Troubleshooting non-functional circuit breaker or timeout configuration in your application. Circuit breakers and timeouts are essential for building resilient applications, especially when interacting with external services or resources like GitHub. When these configurations fail, your application can suffer from cascading failures, resource exhaustion, and poor user experience. This comprehensive guide dives deep into the common causes of non-functional circuit breaker and timeout configurations, providing detailed explanations, code examples, and troubleshooting tips to help you identify and resolve these issues. Understanding circuit breakers and timeouts. Before we dive into troubleshooting, let's recap the purpose and fundamental principles behind circuit breakers and timeouts. Timeouts. Purpose timeouts prevent your application from waiting indefinitely for a response from an external dependency, example GitHub API. If the dependency takes too long to respond, the timeout triggers, preventing the application from hanging and potentially consuming valuable resources, threads, connections, etc. How they work. You set a maximum allowed time for an operation, example an HTTP request, to complete. If the operation doesn't finish within that time, an exception, example socket timeout exception, connect timeout exception, is thrown. Importance. Resource management. Prevents threads or connections from being held up indefinitely. Improved responsiveness. Allows the application to fail fast and retry or use a fallback mechanism. Prevention of cascading failures. Stops a slow dependency from dragging down the entire application. Circuit breakers. Purpose. Circuit breakers protect your application from repeated failures when interacting with an unstable or unavailable dependency. They prevent your application from continuously attempting to call a failing service, giving the service a chance to recover. How they work. 1. Closed state. The circuit is initially closed, allowing requests to pass through to the dependency. 2. Open state. If a predefined number of failures occur within a certain time window, the circuit breaker opens. In the open state, requests are immediately blocked from reaching the dependency and a fallback mechanism is executed, example returning a cached value, throwing an exception, or redirecting to an error page. 3. Half open state. After a defined period, the retry interval, the circuit breaker enters the half-open state. In this state, a limited number of test requests are allowed to pass through to the dependency. 4. Back to closed state. If the test requests succeed, the circuit breaker returns to the closed state, and normal operation resumes. If the test requests fail, the circuit breaker returns to the open state, and the retry interval resets. Importance. Improved stability. Prevents overloading a failing dependency. Faster recovery. Allows failing dependencies time to recover without being constantly bombarded with requests. Enhanced user experience. Provides a graceful fallback mechanism instead of displaying unresponsive or error-ridden UI. 2. Common causes of non-functional configurations. Here are the most frequent reasons why your circuit breaker or timeout settings might not be working as expected. 1. Incorrect configuration placement. Putting the configuration in the wrong place can render it ineffective. Timeouts, in particular, often need to be configured at multiple levels, example HTTP client, connection pool, socket. 2. Configuration overrides. Different configuration mechanisms can override each other. For example, a default timeout set in code might be overridden by a system-level configuration. 3. Misunderstanding default values * failing to understand the default values for timeouts or circuit breaker thresholds. You might think a timeout is enabled when it's actually set to a very high value or even disabled. 4. Configuration errors, typos, incorrect units, simple typographical errors or using incorrect units, milliseconds versus seconds, can break your configuration. 5. Contextual issues * the context in which the timeout or circuit breaker is applied can affect its behavior. For example, a timeout might not work if it's applied to a non-blocking operation. 6. Implementation bugs * errors in the code responsible for implementing and managing the circuit breaker or timeout logic. 7. Thread starvation / resource exhaustion * if your application is already under heavy load and suffering from thread starvation or resource exhaustion, timeouts and circuit breakers might appear to malfunction because the system is unable to respond to the dependency in a timely manner. 8. Incorrect logging / monitoring * poor logging or monitoring can make it difficult to diagnose problems with your circuit breaker or timeout configuration. 9. Network issues * network latency, packet loss, or firewall issues can cause delays that trigger timeouts and circuit breakers. While not directly a configuration problem, network issues can masquerade as such. 10. Dependency behavior * the external dependency, example GitHub API, might be exhibiting unpredictable behavior, intermittent slowdowns, temporary outages. These variations can make it challenging to fine-tune your timeout and circuit breaker settings. 3. Practical examples and troubleshooting, using Java and Resilience4j. Let's demonstrate how to configure timeouts and circuit breakers in Java using the popular Resilience4j library, and then we'll explore debugging scenarios where these configurations fail to behave as expected. Setting up Resilience4j, Maven / Gradle. First, add Resilience4j as a dependency to your project. Maven *, Gradle *. B code example, GitHub API call with timeout and circuit breaker. Explanation *. Dependencies * we've added the necessary Resilience4j dependencies to our project. Configuration * we define circuit breaker config and time limiter config with specific thresholds and durations. Pay close attention to the values. Decoration * the call github API function is wrapped with both the time limiter and the circuit breaker using the decorate callable methods. Fallback * if the circuit is open or the timeout is exceeded, a fallback mechanism, returning fallback, GitHub API unavailable, is triggered. Simulation * the call github API method simulates network latency or failure to allow us to test the circuit breaker and timeout behavior. Main method, the main method calls get GitHub repository info multiple times, so you can observe the circuit breaker state changes and timeout exceptions. See troubleshooting scenarios. Now, let's explore scenarios where the timeout or circuit breaker might not work as expected and how to diagnose them. Scenario 1, timeout not triggering. Problem you expect the timeout to trigger after 5 seconds, but the application hangs for much longer. Possible causes incorrect configuration double check your time limiter config. Make sure the timeout duration is set correctly, example duration of seconds, 5. An extra 0 can cause issues. Timeout override another configuration mechanism, example JVM level socket timeouts, HTTP client configuration, might be overriding the Resilience4j timeout. Investigate your HTTP client's timeout settings. Blocking operation the call github API method might be performing a blocking operation that the time limiter can't interrupt effectively. Ensure that the operation is interruptible. For instance, interruptible I/O operations from libraries such as Java.neo or OCAT3 should be used. Asterisk concurrency issues. Asterisk if the operation is running on a thread pool, thread starvation can prevent the timeout from being triggered. The thread pool size can be too small or the threads might all be blocked. Asterisk troubleshooting steps. Asterisk 1. Verify configuration. Asterisk print the time limiter config to the console to confirm its settings. 2. Check HTTP client timeout. Asterisk if you're using an HTTP client, example HTTP client, OK HTTP client, Spring Web client, check its connection and read timeout settings. Ensure these timeouts are less than or equal to the Resilience 4J timeout. 3. Logging and monitoring. Asterisk add detailed logging to the call github API method to track how long it takes to execute. Use a monitoring tool, example Micrometer, Prometheus, to monitor the execution time of the method. This will help you pinpoint whether the problem is truly the timeout or something else slowing down the operation. 4. Interruptibility. Asterisk if the call github API method performs I/O operations, make sure they are interruptible. If using the Java.net package, consider switching to Java.neo, or a library such as OCAT3 or Apache HTTP client which provide interruptible I/O. Scenario 2, circuit breaker not opening. Asterisk problem. Asterisk even though the call github API method is consistently failing, the circuit breaker never opens. Asterisk possible causes. Asterisk incorrect configuration. Asterisk the failure rate threshold, sliding window size, or minimum number of calls might be set incorrectly. The circuit breaker needs a sufficient number of calls to evaluate the failure rate. Asterisk exception handling. Asterisk the record exceptions configuration might not be recording the specific exceptions being thrown by call github API. Ensure the exception class or a parent class of the exception is included in the record exceptions configuration. Asterisk exceptions ignored. Asterisk the ignore exceptions configuration might be inadvertently ignoring the exceptions that should be triggering the circuit breaker. Asterisk state management issues. Asterisk there could be a bug in the circuit breaker implementation itself. Asterisk troubleshooting steps. Asterisk 1. Verify configuration. Asterisk print the circuit breaker config to the console. 2. Check exception recording. Asterisk confirm that the exceptions thrown by call github API are being recorded by the circuit breaker. Use circuitbreaker.getMetrics to inspect the number of successful calls, failed calls, and the circuit breaker state. 3. Logging circuit breaker events. Asterisk listen for circuit breaker events, state transitions, etc., to gain more insight into its behavior. 4. Slow call threshold. Asterisk ensure the slow call duration threshold is appropriate for the call that is made to the GitHub API. By default, no call is considered as a slow call. If you want calls to be considered as slow call, and recorded by the circuit breaker, set slow call duration threshold to an appropriate value. Also slow call rate threshold should be configured. 5. Minimum number of calls. Asterisk the minimum number of calls property defines the minimum number of calls which are required, per sliding window duration, before the failure rate threshold or slow call rate threshold calculation is performed. If the sliding window duration is set to 10 and only 3 calls are registered, with 3 failures, then the circuit breaker won't trip open. Scenario 3, circuit breaker opening too quickly. Asterisk problem. Asterisk the circuit breaker opens after only 1 or 2 failures, even though you've configured it to require more failures. Asterisk possible causes. Asterisk small sliding window. Asterisk the sliding window size is set too small. If the window only holds a few calls, even a single failure can push the failure rate above the threshold. Asterisk fast failure rate. Asterisk the failure rate threshold is set too low. Even a small number of failures can trigger the circuit breaker if the threshold is very low. Intermittent failures. If failures are intermittent, example due to network blips, the circuit breaker might open and close repeatedly, causing unnecessary disruptions. Troubleshooting steps. 1. Adjust thresholds. Increase the sliding window size and / or the failure rate threshold to make the circuit breaker less sensitive to transient failures. 2. Introduce delay. Consider adding a small delay before retrying failed requests to allow the dependency to recover. 3. Monitor state transitions. Use the circuit breaker.get event publisher to monitor state transitions and determine how frequently the circuit breaker is opening and closing. 4. Automatic transition from open to half open enabled. Consider disabling the automatic transition from open to half open via setting automatic transition from open to half open enabled to false. If it is disabled, you can manually call the transition to half open method on the circuit breaker instance. 4. Best practices for circuit breaker and timeout configuration. Start with reasonable defaults. Don't start with extremely low timeout values or highly sensitive circuit breaker settings. Begin with reasonable defaults and gradually adjust them based on observed behavior. Monitor and tune. Continuously monitor your application's performance and the behavior of your circuit breakers and timeouts. Use metrics and logging to identify areas for improvement. Consider latency variability. Account for the variability of network latency and dependency response times when setting timeout values. Use percentiles or other statistical measures to choose appropriate timeout values. Use asynchronous operations. Whenever possible, use asynchronous operations, example completable future in Java, to prevent blocking the main thread. This is crucial for effective timeout management. Implement fallback mechanisms. Always provide a fallback mechanism, example returning cached data, displaying an error message, when the circuit breaker opens or a timeout occurs. Test thoroughly. Test your circuit breaker and timeout configurations under various load conditions and failure scenarios. Use engineering principles to simulate real-world failures. Document your configurations. Clearly document your circuit breaker and timeout settings, including the rationale behind the chosen values. V. Advanced considerations. Bulkheads. Bulkheads limit the number of concurrent requests to a dependency. This prevents a single failing dependency from overwhelming your application. Resilience4j provides a bulkhead module. Rate limiters. Rate limiters control the rate at which requests are sent to a dependency. This helps prevent your application from exceeding the dependency's rate limits and being throttled. Resilience4j provides a rate limiter module. Spring Cloud Circuit Breaker. If you're using Spring Cloud, consider using the Spring Cloud Starter Circuit Breaker dependency, which provides a higher level abstraction for circuit breakers, using libraries like Resilience4j or Hystrix under the hood. 6. Conclusion. Configuring timeouts and circuit breakers effectively is crucial for building resilient and reliable applications. By understanding the principles behind these patterns, carefully configuring the appropriate parameters, and diligently monitoring their behavior, you can protect your application from cascading failures and ensure a better user experience, even in the face of unreliable dependencies like the GitHub API. Remember to combine these techniques with robust error handling, logging, and monitoring for comprehensive resilience. The key is to test and adapt to the specific characteristics of your application and its dependencies.